So, going to have review of chapters 5, 6, and 7 today. The test on chapters 5, 6, and 7 is on Wednesday, the 10th. You get one sheet of notes, double-sided. You will need a calculator. The lab on Wednesday is for makeups. I've put zeros in for all the unfinished labs at this point. So if you have any zeros on your labs, that's the one you need to make up. Just so you have a better idea of what you're doing. So we'll start with chapter 5 on heat. Oh, things work better when they're turned on. Let's start with temperature. Temperature is a measure of the average kinetic energy of a substance. There are a number of different temperature scales. The ones we'll be using in this class are degrees Celsius, degrees Kelvin, and degrees Fahrenheit. Degrees Celsius and Kelvin have the same size, but different zeros. So to convert from Celsius to Kelvin, you add 273, moving the zero to absolute zero. And to convert from Kelvin to Celsius, you subtract 273, moving from absolute zero to moving the zero from absolute zero up to the freezing point of water, because water freezes at 273 Kelvin, which is 0 degrees Celsius. To get Fahrenheit from Celsius, you multiply the temperature in Celsius by 1.8 and then add 32 to adjust the 0 point. To go the other way around, you take the temperature in Fahrenheit and subtract 32 and then divide by 1.8 to get the temperature in Celsius. So here's an example problem. What's 30 degrees Celsius in Fahrenheit? Temperature in Fahrenheit is 1.8 times temperature in Celsius plus 32. 1.8 times 30 plus 32 gives you 54 plus 32, or 86 degrees Fahrenheit. For Fahrenheit degrees and for Celsius degrees, you need the degree symbol. It's actually optional for Kelvin. So Kelvin degrees can be written as just capital K as a unit. Heat is energy that's transferred from one object to another as the result of a temperature difference. So heat is energy in transit because of some difference in temperature. And heat is energy, so the unit for heat would be joules. However, we also use a calorie, which is a unit developed for heat before we knew that heat was energy. And a calorie is the amount of heat required to raise 1 gram of water 1 degree Celsius at normal atmospheric pressure. So 1 calorie is about 4.2 joules, so 4.186 joules. That will be given as a conversion factor for the exam. 1 kilocalorie is the heat necessary to raise 1 kilogram of water by 1 degree Celsius. 1 food calorie is 1,000 calories, or 1 kilocalorie. So the calories you see on your food are not the same as actual lowercase c calories. 1 food calorie is 4,186 joules, or about 4.2 kilojoules. I will be clear about food calories versus regular calories. So how many joules are in a 300 food calorie chicken sandwich? 1 food calorie is 1,000 calories. So 1 calorie is 4.186 joules. 300 food calories is 300,000 calories. 300,000 calories times 4.186 joules over 1 calorie gives us 1,255,800 joules. Rounded to 3 significant figures is 1,260,000 joules, or 1.26 times 10 to the 6 joules. Now, the energy needed to change the temperature of something without changing its state, just warm it up or cool it down, is determined via the specific heat. So the heat required to cause a change in temperature, delta T, is the mass of the substance times the specific heat capacity of the substance, C, times the change in temperature. And this equation applies when you have something that is not undergoing a phase change. It is undergoing a phase change, you'll also have to bring into account latent heat. But the heat required to warm up or cool down is the specific heat. So, as a problem, how much heat does it take to warm 3 kilograms of water with a specific heat capacity of 1 kilocalorie per kilogram degree Celsius from 12 degrees Celsius to 32 degrees Celsius? So, heat is mass times heat capacity times change in temperature. Our change in temperature is going to be our final temperature minus our initial temperature. We're going up by 20 degrees. So our mass is 3 kilograms. Our heat capacity C is 1 kilocalorie per kilogram degree C. And our change in temperature is 20 degrees C. So this 3 times 1 times 20, that's 60 kilocalories. Any questions? Latent heat is the energy needed to change the phase of something, i.e. melting it or boiling it. The latent heat of fusion is the energy required to melt it. The heat required to melt something is its mass times the latent heat of fusion. The latent heat of vaporization is the heat required to boil something. The heat required to boil a substance is mass times the latent heat of vaporization. Substances give off their latent heat when they go the opposite direction. So when something freezes, you need to remove that much heat. When something condenses, it releases that much heat. So one of the ways the atmosphere is warmed is by water condensing into clouds. It actually warms up the atmosphere around it because it releases that heat. So how much heat does it take to melt 2.5 kilograms of ice at its melting point of 0 degrees Celsius? The latent heat of fusion for ice is 80 kilocalories per kilogram. So this is, again, quite straightforward. Heat is mass times latent heat of fusion. So 2.5 kilograms times 80 kilocalories per kilogram gives you 200 kilocalories. So it's important to pay attention to units here. Because if you wanted to write this in calories, it would be 200,000 calories, and so on. So just make sure you use the right units based on what information you're given. Now, when you have a confined gas, the pressure of a confined gas is affected by, it's directly proportional to the number of molecules, N, and the Kelvin temperature, T, and it is inversely proportional to the volume, V. So pressure is proportional to N times T over V. T here is specifically the temperature in Kelvin. So if you want to figure out what pressure is, P2 over P1 will equal V1 over V2 times T2 over T1. And this is when N is constant, but for all the problems I'll give, N will be constant. And if something is not changing, if it's fixed, that term goes to 1. Now, the full form of the ideal gas law is PV equals nRT. But you don't need to worry about that for the test. So if you take a sealed, rigid container of helium gas at 77 Kelvin and a pressure of 1 times 10 to the 5th pascals, and you warm it up to 308 Kelvin, what will the pressure be? So sealed, says N is fixed. Rigid says volume is fixed. And temperature is changing and pressure is changing. And you can see here I gave temperatures in Kelvin. And you might notice here I didn't put a degree symbol for Kelvin, because you can do that. But only for Kelvin. Degrees Celsius and degrees Fahrenheit both need the degree symbol. Otherwise, they're different units. Both of them electrical, actually. One is the unit for charge, the other is the unit for inductance. Inductance. So N is fixed and V is constant. It's sealed and rigid. P2 over P1 equals V1 over V2 times T2 over T1. So P2 over P1 equals V1 over V2 times T2 over T1. But the volume doesn't change. So this term here goes away. So P2 over P1 equals T2 over T1. We can multiply both sides by P1. And P2 equals P1 times T2 over T1. P2 is thus going to be P1, 1 times 10 to the 5th pascals, times 308 Kelvin divided by 77 Kelvin. 308 over 77 is 4. So P2 times 10 to the 5th pascals. And this is another one where you need to make sure you're using the right units. If it's asking about pressure, it's going to be whatever pressure units were given in the problem, because there's like a billion of them. There are changes with temperature. In general, most matter, solids, liquids, and gases will expand with an increase in temperature and contract with a decrease in temperature. Big exception to this is water. Ice floats. Heat transfer occurs in several ways. You have conduction, which is the flow of heat, through contact, through a substance directly through contact. You have convection, which is the flow of heat being carried by a moving substance. So your stove has a burner that gets hot. That heats through conduction. The water in the pot of water you're boiling moves and heats the top of the water through convection. The hot water rises, the cool water sinks. Or your house or this building is heated by convection, forced convection, where there's a fan. You may have heard of a convection oven or an air fryer. They have the convection oven because they have a fan that moves the air around, which transfers the heat faster, which cooks things faster. And then lastly, there is radiation. Heat transferred by radiation is just, it's heat transfer by light, infrared light, generally. So conduction is transfer of heat by molecular collision. How well substance conducts depends on the molecular bonding. Metals tend to conduct very well. Things with gases and liquids tend to conduct poorly. Thermal conductivity is a measure of a substance's ability to conduct heat. Liquids and gases are generally poor thermal conductors because their molecules are further apart, particularly gases. Metals are generally good thermal conductors because their molecules are close together. Water is not a great thermal conductor, but it's good at convection, and it stores a lot of it. It has a very high specific heat capacity, so it's very good at burning you. Convection is the transfer of heat by movement of a substance or mass from one position to another. Most homes are conveyed by convection, by the movement of hot air. And radiation is the process of transferring energy by means of electromagnetic waves. Electromagnetic waves will carry energy even through a vacuum. If you've got like a classic space heater, space heaters with the glowing wire, that's radiation. And in general, dark objects absorb radiation well, and light-colored objects do not absorb radiation well. So my shirt absorbs radiation well, my pants, not so much. Thermodynamics deals with the dynamics of heat and the conversion of heat to work, things like car engines and refrigerators, etc. There's 3 laws of thermodynamics. The first law of thermodynamics is just conservation of energy. The heat added to a closed system goes either into the internal energy and or to doing work. You don't create or destroy energy. Heat is energy. So the heat added to a system equals the change in internal energy plus the work done by the system. The second law of thermodynamics says it's impossible for heat to flow spontaneously from a colder body to a hotter body. And this is actually defined in that you get no heat engine operating in a cycle, can be perfectly efficient. It can't convert all thermal energy into work. So 100% thermal efficiency is impossible. You can always convert 100% of heat of work to heat. That's easy. But the other way around, heat to work is impossible. 100% thermal efficiency is impossible. And the third law of thermodynamics is that it's impossible to obtain a temperature of absolute zero. Absolute zero is the lower limit for temperature. So the first law says you can't win, second law says you can't break even, and third law says you can't get out of a game. So a heat engine is something that takes heat from a high temperature reservoir, moves it to a low temperature reservoir, and converts some of it into work in the process. And the efficiency of a heat engine depends on the difference in temperature between the high and low temperature reservoirs. The bigger the difference, the more efficient it can be. That's a consequence of the second law of thermodynamics. But that's a heat engine. The sort of opposite of a heat engine is a heat pump. A heat pump takes work in and pulls some heat from a low temperature reservoir and pumps it to a high temperature reservoir. So a heat pump moves heat from a low temperature reservoir to a high temperature reservoir while taking in some extra work. So there's some additional heat energy required, and additional heat gets dumped in that high temperature reservoir. And this is what an air conditioner does, or your refrigerator. Your refrigerator is a heat pump, and air conditioner is a heat pump. Anything that cools things down is a heat pump. But you can also use a heat pump to heat your house more efficiently because you can pull some energy, some heat from the outside. And heat pumps have sort of the opposite issue of heat engines. They work better the smaller the difference is between the inside and the outside counter. Entropy is tied to the second law of thermodynamics, and the change in entropy indicates whether or not a process can take place naturally. It's associated with the second law. Basically, either if something's going to happen naturally, spontaneously, it either needs to be going to a lower energy state, so energy is released, or going to a higher entropy state, so entropy is increased. So entropy is a measure of the disorder of a system. Most natural processes lead to an increase in disorder. In fact, all processes lead to an increase in disorder of the universe. So to decrease entropy, you have to expend energy, and that's going to increase entropy somewhere else. And because heat naturally flows from high to low, the entire universe will eventually cool down to a final common temperature. This is known as the heat death of the universe. So the important equations from chapter 5, temperature in Kelvin is temperature in Celsius plus 273. Temperature in Celsius is temperature in Kelvin minus 273. Temperature in Fahrenheit is 1.8 times temperature in Celsius plus 32. Temperature in Celsius is temperature in Fahrenheit minus 32 divided by 1.8. The heat required, specific heat, the heat required to change the temperature of an object is mass times heat capacity times change in temperature. That change in temperature is going to be heat divided by mass times heat capacity. Latent heat is the heat required to cause a phase change. It's mass times the appropriate latent heat. And pressure is proportion to NT over V. So P2 over P1 equals V1 over V2 times T2 over T1 times N2 over N1. Because PV equals nRT, where R is a constant. So that was chapter 5. Now on to chapter 6. So waves. The anatomy of a wave, there's a wavelength, an amplitude. The wave travels with a velocity. The amplitude is the maximum displacement from equilibrium. The wavelength is the length of one cycle in distance. The length of one cycle in time is the period. So the distance of one complete wave is the wavelength. The amplitude is the maximum displacement of any part of the wave from its equilibrium position. The energy transmitted by the wave is directly proportional to the amplitude squared. The frequency is the number of oscillations or cycles that occur at a given time, 1 second usually. And the unit to describe frequency is the hertz. And 1 hertz is 1 cycle per second. 5 hertz is 5 cycles per second. 500 kilohertz is 500,000 cycles per second. Now, and so on. The period is the time it takes for a wave to travel a distance of 1 wavelength. Frequency and period are inversely proportional. Frequency is equal to 1 over the period. Period is equal to 1 over the frequency. So what's the frequency of a wave with a period of 0.0001 seconds? Well, frequency is just 1 over period. So 1 over 0.0001 seconds is 10,000 hertz. Since speed is distance over time, well, that's the distance is the wavelength, the time is the period. But 1 over the period is just the frequency. So the speed of a wave is wavelength times frequency. And that means if you want to find the frequency, when you know the speed and the wavelength, frequency is speed divided by wavelength, and wavelength is speed divided by frequency. Period of wave is 2, yeah. So here we have the same frequency, but different velocities. So when we have a high wave velocity, the wavelength is longer. When we have a low wave velocity, the wavelength is shorter. So what's the wavelength of a wave with frequency 20 hertz and speed 40 meters per second? Well, speed is frequency times wavelength. The wavelength is speed over frequency. The 40 meters per second divided by 20 hertz gives us 2 meters. Now, electromagnetic waves are vibrating electric and magnetic fields that oscillate perpendicular to each other in the direction of wave propagation. They are light. The field energy radiates outwards at the speed of light c. And the speed of all electromagnetic waves in a vacuum is c, which is 3 times 10 to the 8th meters per second. And to a good approximation, this is also the speed of light in air. Now, the human eye is only sensitive to a very small portion of all the electromagnetic waves out there, which vary from at the shortest wavelengths, gamma rays, to the longest wavelengths, radio waves. We only see stuff between 400 nanometers and 700 nanometers, which is a very small portion, because gamma rays are tiny. They're like picometers or smaller. And radio waves can be kilometers. So what's the frequency of a radio wave with a wavelength of 1.5 meters? Remember, the speed of light is 3 times 10 to the 8th meters per second. So here, the speed of light c equals frequency times wavelength. Frequency is going to be the speed of light divided by wavelength. So 3 times 10 to the 8th meters per second divided by 1.5 meters gives us 3 times 10 to the 8th hertz. So that's 200 kilohertz. Oh, no, sorry, 200 megahertz. I'm losing my head right. So that's a bit higher than FM radio. FM radio is in the 2 to 3 meter range. Now, loudness is a relative term, but intensity is quantitative and is a measure of the amount of energy transferred through a given energy area. We can measure intensity in joules per second per square meter or watts per square meter. For sound, the threshold of hearing is around 10 to the minus 12 watts per square meter, and an intensity of about 1 watt per square meter is painful. Intensity decreases with distance from the source as 1 over the radius squared. So if you double the distance, you quarter the intensity. Sound intensity is measured on the decibel scale. 1 decibel is 1/10 of a bell. And the bell is a unit of intensity named in honor of Alexander Graham Bell, and is a logarithmic scale. It's not linear with respect to intensity. And therefore, when the sound intensity is doubled, the decibel level is only increased by 3 decibels. And the actual formula to go, if you want to find out the intensity in like watts per square meter from the intensity in decibels, if I remember correctly, if you have your intensity in decibels, with decibels divided by 10 minus 12, that's how the decibel scale is. So you can see if you go up by 10 decibels, this increases by a power of 10. So that 1 watt per square meter is at 120 decibels. So how many times more intense is a 32 decibel sound than a 12 decibel sound? Well, first, let's look at the difference. So every 10 decibels corresponds to an increase in intensity by a factor of 10. So 32 decibels compared to 12 decibels, the difference is 20 decibels. Plus 10 decibels is 10 times the intensity. Plus 20 decibels is 10 to the 2 times the intensity. So that's 100 times more intense. So every additional, the Doppler effect is the apparent change in frequency resulting from relative motion of the source and the observer. As you have a moving sound source approaches an observer, the waves in front get bunched up, the waves behind get spread out due to the movement of the sound source, and the observer will hear a higher pitch, shorter wavelength as the sound source approaches, and then they hear a lower pitch, a longer wavelength as the sound source departs. They pile up in front of the moving object and spread out behind. As you approach, the waves get bunched up, you get higher frequency. Behind, the waves are spread out, you get lower frequency. A standing wave is a stationary waveform arising from the interference of waves traveling in opposite directions. Along a rope or string, for example, waves will travel back and forth. And when these two waves meet, they'll constructively interfere with each other, forming a combined and standing waveform. So here's an example of a standing wave. This is 60 centimeters in length for the string. Here you can see there's half a wave. So the wavelength is 120 centimeters. Here you have 2 antinodes. This is a whole wave. So the wavelength is 60 centimeters. Here you have 3 antinodes. This is 1.5 waves. So the wavelength is 40 centimeters. The formula is 2 times the length divided by the number of antinodes, the number of big walls. And resonance is a wave effect that occurs when an object has a natural frequency that corresponds to an external frequency. And if you have a pair of a driving force with a frequency equal to one of the natural frequencies, that thing will be driven. So a common example is pushing a swing. You have to push in time with the swing to keep the swing going. Or jump rope. And a more dramatic example is singing at the resonance frequency of a wine glass loud enough to shatter it, which is something you can do. So important equations. Frequency is 1 over period. Velocity is frequency times wavelength. The speed of light is 3 times 10 to the 8th meters per second. And now let's talk about optics. So the law of reflection is that the angle of refraction is equal to the angle of incidence. So the reflected and incident waves will also be in the same plane. They'll be at the same angle from the normal. So if you have a beam of laser light that hits a flat pane mirror at 35 degrees to the normal, what angle does the light reflect at? Well, angle of incidence equals angle of reflection. So angle of reflection will equal the 35 degrees of the angle of incidence. Now, refraction is the bending of light waves caused by a speed change as light goes from one medium to another. So it's the deviation of light from its original path because of a speed change. The index of refraction is the ratio of the speed of light in a vacuum to the speed of light in a medium. Index of refraction n is speed of light in a vacuum divided by speed of light in that substance. So what's the speed of light in the material with an index of refraction n of 3? Well, n is speed of light in the substance, in the vacuum divided by speed of light in the medium. So speed of light in the medium is the speed of light divided by the index of refraction. So 3 times 10 to the 8th meters per second divided by the index of refraction 3 gives us a speed of light in the medium of 1 times 10 to the 8th meters per second. And if you want to go the other way around, like you will divide them. Now reflection, because of when light goes from a denser medium, when light goes from a less dense medium to a more dense medium, the angle of it will get closer to the normal, and it will be the opposite when it goes from a higher index of refraction medium to a lower index of refraction medium. The angle from the normal will get bigger, which means that there is a certain critical angle where the angle of refraction is 90 degrees to the normal. So for any angle greater than that, you get total internal reflection. No light goes out, the light just gets reflected. Dispersion is the way you separate light out into individual wavelengths by the fact that the index of refraction is not the same for all wavelengths. So it varies slightly according to the wavelength of the light. So when visible light is refracted, the different wavelengths from about 400 to 700 nanometers of light are bent at slightly different angles. Therefore, you can disperse visible light into a spectrum of colors. So dispersion is how you create rainbows with a prism. So refraction of different wavelengths result in visible light being dispersed into its full spectrum of colors, blue, green, red. And notice how the shorter wavelength gets refracted more than the longer wavelength. That's what happens with glass prisms. Then let's talk about spherical mirrors. For a spherical mirror, it has a focal point halfway between the center of curvature and the mirror. So it has a focal length from the mirror equal to half the radius. So the focal length is the radius divided by 2. So if a spherical mirror has a radius of 25 centimeters, what's its focal length? Just going to be the radius divided by 2. 25 centimeters divided by 2 is 12.5 centimeters. Now, when you form an image with a mirror or a lens, there are certain characteristics. The image can be real or virtual, it can be upright or inverted, and it can be larger or smaller than the object. Now, it turns out real images are always inverted and virtual images are always upright. And larger or smaller depends on the relative position of the object in the image. So the image characteristics are determined by several criteria, including the object distance, the distance of the object from the vertex, the focal point or focal length of the spherical mirror, and the size and orientation of the object. And the distance of the image from the vertex is called the image distance. So here's an example of an object forming a real image. So if an object is beyond the center of curvature of a converging mirror, it will form an inverted real image that is smaller than the original object. If an object is between the focal length and the center of curvature with a converging mirror, it will form an inverted real image that is larger than the object. That's what's happening right here with the projectile. And then lastly, if the object is closer to the mirror than the focal length, it will create a virtual upright image that is larger than the object. Now, for a diverging mirror, the object is always upright, virtual, and smaller than the object. And the mirror formula is 1 over the focal length equals 1 over the distance to the object plus 1 over the distance to the image. Focal length is positive for concave or converging mirrors, and negative for convex or diverging mirror. DO is the distance from the mirror to the object. DI is the distance from the mirror to the image. Negative distances are virtual images on the far side of the mirror for DI. And if DI is bigger than DO, the image is bigger than the object. If it's smaller than DO, the image is smaller than the object. So if an object is placed at a distance 3 centimeters, from a convex mirror of focal length -2 centimeters, where is the image? 1 over focal length equals 1 over DO plus 1 over DI. So -1/2 equals 1/3 plus 1 over DI. So -1/2 minus 1/3 is -5/6. That's 1 over DI. So DI is going to be 1 over that. So -6/5, which is -1.2 centimeters. So the image is virtual, 1.2 centimeters behind the mirror, and it will be upright. Now lenses are similar to mirrors. Rays parallel to the principal axis will converge at the focal point on the opposite side of the lens. So the big difference with lenses is positive image distances and real images are on the far side of the lens from the object instead of on the same side like with a mirror, because there's no reflecting going on. So for a converging lens, if the object is beyond the focal length, you get an inverted real image formed. The image becomes larger as the focal point is approached. The image will become bigger than the object when it's between the focal point and twice the focal length from the lens. Inside the focal length, the object will always form a virtual image on the object side of the lens. which will be bigger than the object. This is what's happening with a magnifying lens. And for a diverging lens, the image is always upright, smaller than the object, and virtual. The lens formula is 1 over the focal length equals 1 over DO plus 1 over DI. Focal length is positive for converging lenses, negative for diverging lenses. DO is the distance from the lens to the object. DI is the distance from the lens to the image. Negative image distances are virtual images on the near side of the lens. So if an object is placed at a distance of 20 centimeters from a converging lens of focal length 10 centimeters, where is the image? 1 over focal length equals 1 over DO plus 1 over DI. So 1 over 10 equals 1 over 20 plus 1 over DI. 1/10 minus 1/20 is 1/20. That equals 1 over DI. So DI is at plus 20 centimeters. And because the distances are the same, the image will actually be the same size as the object. Image is real, 20 centimeters from the lens on the side opposite the object. The human eye has a converging lens that makes an upside down real image on your retina. And since the distance to the objects varies, the focal length of the lens has to vary because the image distance doesn't. And this is done with the ciliary. The image forms in front of your retina, and glasses with diverging lenses can correct this. And farsightedness is when your focal length is too long. You can see distant objects clearly, but not nearby objects. The image forms behind the retina, and glasses with converging lenses correct this defect. This is what reading glasses are for. Polarization is a preferential orientation of the field vectors. The polarization of light can be attained by several means, the most common of which is a Polaroid film, like this. Type of polarizer only allows the components of waves in a specific plane to pass. Pretty sure this one polarizes vertically. And then if I have another one that also polarizes vertically, rotate it so it polarizes horizontally, blocks all of them. And the human eye cannot detect whether light is polarized or unpolarized, or how it's polarized. So if you have a polarizer, then you have an analyzer, and they're in the same direction, you'll get transmitted polarized light. Here you have a polarizer and an analyzer at right angles, you'll get no light. Diffraction is the bending of waves around corners and such when moving past an opening or obstacle that has a size smaller than or equal to the wavelength. All waves, sound, light, water, etc., show this type of bending as they go through relatively small slips or pass by the corners of objects. The larger the wavelength compared to the size of the opening or object, the greater the diffraction. When two or more waves meet, they add up, and they're said to interfere with each other. The resulting waveform is a combination of the individual waves. This is the principle of superposition. The combined waveform is given by the sum of the individual waves. And when interfering, it's possible for two waves to reinforce or cancel each other out. So here is reinforcing, here is canceling each other out. Sorry, the circles are slightly off. So, important equations from this chapter. Index of refraction is the speed of light in a vacuum divided by the speed of light in the medium. The focal length of a spherical mirror is its radius divided by 2. To find the location of an image for a mirror, it's 1 over the focal length, is 1 over the distance to the object, plus 1 over the distance to the image. Negative focal length is a diverging mirror. Negative image distance is a virtual image. To find the location of an image for a lens, same formula. Negative focal length is diverging lens. Negative distance to the image is a virtual image. So that is the review. Are there any questions? So tests, much like the previous tests, but covering 3 chapters instead of 2. It'll be on Wednesday in lecture. Lab on Wednesday is for makeups. And yeah. And if you've taken the chapter 7 quiz, I got those graded because I'm trying to get everything graded. But I'm not handing back because not everyone's taking it. But yeah, I think that is all. I'm gonna end this. I'm gonna end the meeting.